I welcome you to look through a physicist's glasses, see the world a bit differently. To better see what I want to tell you about today, it is a wise choice to start with standing on the shoulders of giants. This time, Richard Feynman, who is known for explaining simply yet correctly. If, in some cataclysm, all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world if just a little imagination and thinking are applied. Richard Feynman. I will add to the atomic hypothesis a second, let's say Avogadro's hypothesis, that there is an astronomical amount of these little particles around which are counted using Avogadro's constant. I want to show you how much of the world we can start to understand with just two simple hypotheses, such that you would feel it in your bones and would see it as something more than just an interesting fact. First, how do we know that something is really true? If a physicist would want to be precise, he would avoid words like this nail is 5 centimeters long, but rather this nail is approximately 5 centimeters long. This isn't your everyday approximately, since when being asked how precise, a physicist can answer, oh, with 5% error. All we can do is reduce this error until it's so small that some other error is bigger. Sadly, the world is more complicated than our experiments. But that doesn't mean that we cannot be certain. You might have heard that quantum mechanics is the most precisely tested theory. So, how certain are we? Let's look at the dimensionless constant called the fine structure constant, alpha, that is important when talking about atoms. Answering why is for another day. But more importantly, it is also astonishingly precisely known. In recent experiments, it has been determined with a relative accuracy of 81 parts per trillion. Probabilities, especially such low ones, are quite hard to wrap your head around. A different way to think about the probability is, what are the odds that we do an experiment that predicts a different value for the fine structure constant? Let's compare with flipping a fair coin that has equal probability to land on heads or tails. What are the odds that we get heads once? 50%. What if we get heads twice in a row? 25%. 3 times? 12.5%. Each time the probability is halved. Then it is more likely to flip a coin 34 times in a row and every single time getting heads than it is to make an experiment and get a slightly different value for the fine structure constant. This is just one example, but we can definitely see that physicists can be confident that something is correct. So, let's not take our chances with flipping the coin, and let's see how profound are the two hypotheses. Atomic hypothesis. The idea that everything is made of small little particles is nothing new, and even the ancient Greeks thought of this. You can intuitively believe the atomic hypothesis. We can divide a cake in half, then half again, until it cannot be seen by the human eye, then a microscope, and eventually reaching the indivisible particle, atomos, uncuttable in ancient Greek. Democritus had an argument for this. If you could infinitely cut something up, then you would be left with points that have no volume. But then, how can you create volume by adding up something that doesn't have any? While the atomic hypothesis is plausible, the ancient Greeks didn't know for certain that it is true, nor they didn't know what the uncuttable atom was. With modern science, we have confirmed the atomic hypothesis, and we know how certain physicists can be. While we know in much more detail about the atom, it will be enough to imagine it as a very tiny ball. And just like Richard Feynman said, these little balls are in perpetual motion, always whizzing around. But how tiny these particle balls are exactly? One way would be to count them all up, and it will be a doozy. As I called it, the Avogadro's hypothesis relates to the Avogadro's constant. Avogadro's constant might seem daunting, but think of it as a different way of counting. In the same way, we can call 12 eggs a dozen of eggs. In this case, a word mole is used, and 1 mole contains approximately 6.022 times 10 to the 23rd atoms. We're done, right? While physicists often deal with big numbers, not everyone is a physicist. Just like before with the coin, let's try to compare this number to get a feel for the size of Avogadro's constant. Let's find 1 mole in the wild, meaning how much is 1 mole? Looking at a familiar plastic container, the plastic water jug used in water dispensers. They come in different sizes, usually as 5 gallons or approximately 18.93 liters. This should be close enough, as simple air or any other mixture of gases in NTP takes up approximately 24.04 liters. NTP means normal temperature and pressure, namely 20 degrees Celsius and pressure of 1 atmosphere. These are normal conditions, so if you would see an empty plastic water jug, then it probably will be close to NTP. Since Avogadro's constant is so huge, most deviations from NTP or even the size of the water jug wouldn't cause a big error. To make the comparison, first take a normal 1.5 liter Coca-Cola bottle. Then keep adding them side to side until you create the Earth out of 1.5 liter bottles of Coca-Cola. Not just the surface, but the whole Earth. Then, in our Coca-Cola Earth, there are the same, approximately, number of bottles as there are atoms of air in a single empty plastic water jug. 1 mole of particles. If you have the feeling that this is huge, that is too much, I can't even grasp it, that's completely fine. Avogadro's constant is so huge that knowing this much can be good enough. Alright, now I have introduced the 2 hypotheses, atomic and Avogadro's. I have also convinced you why there is a reason to trust these hypotheses. That's the first part of the story. Everything is made of atoms. Now it's time for the so what? Since everything is made of atoms, more generally particles, we can use our hypotheses in many areas. Let's keep it simple and familiar for now. Temperature. It's something that every one of us has definitely seen and experienced. We have our own body temperature, the outside can be sunny, and on rainy days our houses can get cold. We now have the tool to explain temperature. Atoms, the first hypothesis. First, let's consider an analogy. You are colder if you simply stand around, but you heat up when you start running around. We are much more complex than atoms, but here's the idea. When an atom is moving, it has more energy, kinetic energy in particular, that we experience as temperature. Since we know it's quite cramped for these little atoms, there is a huge amount of them, counted in moles using Avogadro's constant. That's the second hypothesis. It's only a matter of time until one quick atom collides with another. As mentioned before, we can think of atoms as small little balls. So what happens when you throw a ball at a stationary ball? You hit the ball away. The ball you threw transferred kinetic energy to the stationary ball. Basically, it now moves. The easiest jump from how individual atoms interact to, say, 1 mole of atoms is to look at a gas, for example air. In gases, the particles are like individual balls, always whizzing around. It gets trickier in liquids and solids, but the main difference is how connected these particles are. In liquids, particles stay together for the most part, but are not forced to stay with their neighbors. They can travel the world. Clearly, the water can flow. When water freezes, these particles settle down. They have their own place in the ice cube, and they have their neighbors. And this time, they'll have to live together with them. Well, until you heat the ice. You can see how, just knowing the seemingly simple atomic hypothesis, we can start to explain why there are three usual states of matter: gases, liquids, and solids. What's the difference between all three? It's a fun exercise to understand how boiling works, and you have the tools to reason about it. I'll leave it as a homework for you to ponder about. But let's consider a gas and finish the story about temperature. Thus far, we have used the atomic hypothesis a lot. But let's try to explain the second law of thermodynamics in gases using the second, Avogadro's hypothesis. You might be scared of the serious second law of thermodynamics, but there is a simple version of it that will be good enough for us now. Heat flows from hotter objects to colder objects. But why? Let's imagine that you are in your nice, small, warm room behind closed doors. All of the windows to the outside are closed, so no heat escapes or enters. Now, you're feeling a bit hot. You heated the room up with your body heat. So you open the door to the rest of the house that is a bit colder. Even if there is no airflow, your room will be cooled down. Why? Since your room is warmer, the air in your room moves around more, has more kinetic energy. It quickly starts to collide with the cold air in the rest of the house. It's not an equal exchange between the hot and cold air particle. Similarly to how throwing a ball on a stationary ball will send it flying, all the while slowing the thrown ball a lot. The cold or the slow one will get faster or hotter, and inversely for the hot particle. Hey, this sounds a lot like the second law of thermodynamics. To tie the whole situation together and move up from these simple collisions to your room cooling down, think of what's likely to happen if you do these collisions a lot. The second, Avogadro's hypothesis, is a guarantee that something unusual won't happen, since there are so many particles, which means that there is a huge number of collisions happening each second. These are the two simple building blocks. Everything is made of little atoms, and there's a lot of them. When we add something extra, like just now, that these little atoms are in perpetual motion and colliding with each other, we can start to understand physical phenomena. Using the perpetual motion of atoms, you can explain why materials generally expand when heated, or how liquids turn into gas. When we think more about the collisions, you can reason how pressure arises. Going out of our comfort zone, if you consider that atoms have electrons, negatively charged particles that can leave the atom, we can see why electric currents can flow, or how your fridge magnet works. Keep looking at the world with wonder and excitement, with a goal to understand it, for you have the keys to make the first steps. Using these two simple building blocks, atomic and Avogadro's hypothesis, you will see there's an enormous amount of information about the world if just a little imagination and thinking are applied. Hopefully, you will now see the world slightly differently now.